There is a specification for the VAM differential amplifier on its common mode rejection ratio. Okay, firstly, what is a common mode rejection ratio? Why is it specified? And how do you ensure that your design has met that specification? Right, a differential amplifier, like the one that we're designing for the VAM input stage, amplifies up the difference between two input signals. In this particular case, I've got a differential amplifier here, and the difference between my two input signals I've just set to be 1 volt by putting this voltage source in here. So one of my inputs, being measured by the voltmeter here, is at 0 volts. The other input is at 1 volt. We have a differential input, that's VA minus VB, if you like, of 1 minus 0 or 1 volt. That is being amplified up by the differential amplifier, which has a gain of 3, because its gain is 30k divided by 10k, or 3, and that is producing an output of minus 3 volts. Minus 3 because the way I've wired it up, the negative input going into the inverting input is 1 volt above the input going into the non-inverting input there. So that's all working fine, just as we would expect a differential amplifier to do. It's multiplying up the difference between the two inputs by its gain, in this case 3, and its two inputs at the moment are at 0, minus 1, and that is giving minus 3. That 3 is known as the differential gain. The difference between the two inputs and the output are related by Vout over the difference between the two inputs. I'll call it delta V in. That is the differential gain. However, these circuits also have what's known as a common mode gain. Now, the common mode gain is the gain in terms of the output divided by the input when both of the inputs are connected together, like so. We now have both inputs connected to 5 volts. It's a perfect differential amplifier, so our output now is 3 times the difference between our two inputs, both of which are at 5 volts, so that's 3 times 0, which is 0 volts. And our output is 0 volts. If it wasn't 0 volts, then we could define a common mode gain as the output divided by V in when they are equal, when both of those two inputs are set to the same value, and we'll call that the common mode gain. Right. Ideally, the common mode gain is 0, but for real non-ideal components, it isn't. The common mode rejection ratio is then just the differential gain divided by the common mode gain. Since the common mode gain is ideally 0, the common mode rejection ratio is ideally infinite. However, in many practical cases, that doesn't quite happen. One of the main reasons it doesn't happen for the circuits that we build in the lab is that the resistors we are using are not perfect resistors. They have a 1% tolerance. If you just go to a random cupboard, pick up one of our resistors out of the shelves, it may not be a 10k resistor, it may be 1% above a 10k resistor, in other words, 10.1k. This resistor might be 1% below a 10k resistor, in other words, 9.9k. This could be 27.7k, 1% below 3k. This one could be 30.3k, which is 1% above 30k. And now we no longer have a differential amplifier, at least not an ideal one. We've tried to select two 30k resistors. Oops, that should be 29.7. We've tried to select two 30k resistors, but we've been unlucky. This one is 1% below the nominal value of 30k, and this one is 1% above the nominal value of 30k. Similarly, we've tried to pick two 10k resistors, but we've been unlucky. This is 1% above the nominal, this is 1% below the nominal. We no longer have a differential amplifier which is behaving as we would like. We now have a common mode gain. 5 volts in is producing 147.8 millivolts out. So our 5 volt input our output, 147.8 milli, divided by our 5 volt input, that is our actual common mode gain, and our actual common mode gain would then be 0.1478 divided by 5, 0.02956. I'll just call it 296 for now, because it fits on the screen. The real differential mode gain, it probably hasn't changed very much. We can just check it, put the 1 volt differential signal back in, and indeed 1 volt in is producing the minus 3 volts out, so our differential gain is still the 3 that we would expect. Our common mode rejection ratio, therefore, is 3 divided by 0.0296, which is that which, if you express it in terms of dB, (40.12 dB). So, if I build a differential amplifier like this with an ideal op-amp, and remember, the op-amps in the lab are not ideal anyway, and just resistors that I select randomly from the draws, then if I'm unlucky, I could end up with a common mode rejection ratio of just over 40 dBs. And that's a problem because the specification for this amplifier says that the common mode rejection ratio should be greater than 50 dBs. And I cannot guarantee that if I just pick random resistors out of the draws. Solution: don't pick random resistors out of the draws. Pick 2 resistors out of the draws for your input resistors here and measure them, and check that they are reasonably close in value. Similarly, 2 resistors for these 2 resistors from the draws, measure them, check that they are reasonably close in value, simulate your actual values, and check that your common mode rejection ratio is going to be within the limits as required for the amplifier. It might be worth saying a bit at this point about why there is a specification for the common mode rejection ratio of these amplifiers. And the answer is because it gives you a specification on how well the input stage rejects noise. Quite a lot of the outputs from audio circuits, from high sensitivity microphones, are very, very small, and they are sent over cables in differential mode, which means that you've actually got 2 signal wires in the cable, one of which is going up while the other one is going down, and vice versa. If any noise gets picked up by this cable, maybe from some electrical noise or radio transmission being picked up or something like that, it will tend to be picked up equally by both of the wires in the cable. So you might get a sudden spike of noise like this. If at the receiving end, at your mixer, you have a differential amplifier, which amplifies up the difference between these 2 signals, then it should recover the very small microphone signal and get rid of this noise spike because the noise is equally placed on both of these 2 signals. and if you subtract them, the noise should cancel out. In terms of mathematics, the signal on one of our wires there, I'll call it A, is plus the signal, plus any noise that is being picked up. Our signal on the other wire, B, is -1 times the signal, plus any noise being picked up on the wire. So if we just subtract them and amplify that, the noise cancels out. We just get twice the signal. It's a very common and very effective way to reduce the noise that's picked up on what can be quite long microphone and instrument cables. But of course, to work, we do need an amplifier with a good common mode rejection ratio, so it does eliminate this noise spikes, any signal which appears on both of the input wires. Next time, we'll look at the input impedance.